Hi, everyone. Thanks for joining our webinar today on commercial space products for lower cost satellites. So I'm going to let Steve go ahead and introduce the panel and kick things off.
Thanks, Kristen. So good afternoon, everyone, and welcome to today's Nsrec webinar with Analog Devices. Today's topic will be commercial space products for lower cost satellites, presented by Kristen Chong. We will have time for questions at the end of the presentation, so if you'd like to submit a question for the panelists, please use the Q&A function at any time during the presentation, and we will try to get as many as possible. If we don't get your question, you can reach out to us via the Nsrec booth or by visiting analog.com/space. Kristen Chong joined Analog Devices in 2015 as a product and test engineer on the space team after graduating with a bachelor's in electrical engineering from the University of Texas at Dallas. She later gained responsibility for space products application support in late 2018, and in early 2020 assumed the role of marketing manager for ADI space power management and precision linear products. Also joining us for the discussion are Winston Clark, Chris Chapman, and Sean Darcy. Winston Clark, who is based in Chelmsford, Massachusetts, joined Analog Devices as part of the Hittite Microwave acquisition and has been in the company for 15 years. As marketing manager with the Space Group, he is focused on supporting RF and microwave applications and has responsibility supporting new technology developments covering DC to 110 gigahertz. Chris Chapman is a 22-year employee of Analog Devices based in Greensboro, North Carolina, and has served in marketing, management, and engineering roles. Sean Darcy, Director, Aerospace and Defense supports numerous initiatives at Analog Devices, including commercial space, military products, and subsystems. Sean came to Analog Devices after a 30-plus year career in aerospace and defense, most recently working for two of the world's largest defense companies. He has expertise in systems engineering, inertial systems, isolators, and digital processing. And now with that, I'll pass things off to Kristen to kick things off.
Thank you so much, Steve. So we'll go ahead and get started. So the topics we kind of want to go over today are kind of the agenda of what we're going to discuss. Is we're going to first kind of touch on some of the major trends going on in the space market that are really driving some of the needs for these lower cost alternatives, these plastic alternatives to the traditional QMLV ceramic hermetic packaged products. After that, we're going to kind of go over the difference between things like EP or automotive grade devices versus commercial space, and kind of what commercial space has to offer that other options don't necessarily, or why other options don't necessarily fit the bill for space applications. From there, we'll go over the difference between the different commercial space flows that we have. We have two of them, and compare those to the traditional QMLV type screening. And then at the end, we'll have time for questions. So like Steve mentioned, at any time you can use the Q&A function in Zoom and submit those questions, and we'll get to them at the end. So there are a number of kind of activities and trends going on within the space market that are really driving this need for lower cost and newer technologies, not least of which being the reduction in launch cost with the advent of more numerous commercial launch services. You have rideshare services like those that SpaceX offers that have significantly reduced the cost it takes to get a satellite up into orbit. What used to cost, hundreds of millions of dollars is now tens of millions of dollars and expected to drop further over the next several years. And this has kind of lowered the barrier of entry to allow new players to enter the space market that couldn't enter that market otherwise because of the prohibitive cost of launch. The other kind of big factor in reducing launch costs is that weight is a critical factor in determining the cost of a given launch. And things like small sats and CubeSats have become kind of ubiquitous in terms of kind of these newer applications, whether it be Earth observation whether it be internet for the masses and these high throughput satellites, or other things like that. We have Starlink, there's Kuiper, OneWeb, Telesat. There are all of these different players kind of going after this market right now. And these small sats are becoming a more widely accepted solution for even some of some things like military grade applications, whereas before they were kind of relegated to more science missions and kind of onesie twosie type of university research projects. So they're becoming more and more common. And they tend to be much larger in order to cover a larger area of space if you're flying in LEO orbit. What would take you, 10 or so geosatellites to cover the entire planet, you now need hundreds or sometimes even thousands to get the same amount of coverage and the same kind of field of view. And with that, kind of going back to the idea of high-speed internet, there's more people demanding more data at faster rates than ever before, especially with the advent of things like 5G. And so the ability to provide those kinds of speeds only really comes from using things like the latest and greatest IC technology available in the market today. And historically, space application or space products have been 1 or 2 generations behind because of the development time that is typically taken to get these parts out into the market. And so we're seeing a much higher demand for these newer products in space applications, and in turn, customers' development times are becoming shorter as well. And so all of those things kind of pooled together have led to this need to really either commoditize the costs for developing satellites or reduce any cost wherever possible to get these things up on orbit. There are a couple of different options that are available kind of before commercial space kind of came around. You could look at either enhanced military plastic or enhanced plastic, or you could look at automotive grade devices. And there's some benefits to those two options above the standard kind of off the shelf regular commercial grade products. With enhanced products, for example, you have extended temperature qualification. You've got, in some cases, 100% temperature testing and traceability down to the wafer lot level, all of which are relatively important for a space application. You have tighter process controls and some additional inspection operations with the addition of kind of a single fab and assembly test site, which are all kind of important for maintaining that confidence in the reliability of the devices, that they're going to survive over a long period of time. Automotive grade kind of offers a similar group of benefits. They're these super low, high volumes with low parts per million defect rates, which can be extremely attractive for space applications. Automotive grade devices go through extremely rigorous qualification standards and extended temperature qualifications as well. But the kind of downfall to automotive is that catalog tends to be extremely limited to what can achieve those extremely rigorous qualification standards, or what kind of electronics are useful for automotive electronics, which may not necessarily mesh 100% with what someone needs for a satellite signal chain. But probably the most important thing to note is that with either of these options, the customer has to assume any and all risk that comes with radiation performance. None of these existing options actually screen for radiation. You might have some level of single event upset when it comes to automotive, but that's about the most that you get. When it comes to total ionizing dose, there is no coverage whatsoever, and any of that can kind of risk voiding the warranty that comes with the devices as well. So that risk can be relatively significant. And even if you go, say, radiation test a given product beforehand to make sure that it's okay for radiation, there could be slight process variations that, although they may not affect the apparent electrical performance of the device, they can have a much more significant effect on the radiation performance. So what may appear to be a product that works just fine, maybe the next radiation lot maybe the next wafer lot that you get is not so great. And so that's kind of one of the things that we intend to address with commercial space products. And Now we'll kind of go over the different screening flows that we have available for commercial space. So we have two of them. There's commercial space low and commercial space high. And then we're also going to kind of compare against what we've used in the past for traditional space QMLV type products. Starting with commercial space low, it's the lowest cost of the two, obviously implied by the word low. And it's really intended for high volume or LEO constellations where your risk tolerance might be a little bit higher than that of, say, a geosynchronous orbit where radiation is a more significant concern. You can't say that radiation is not a concern in LEO, but it's certainly not as severe as it would be at higher orbits. You get single wafer fab location, as well as that wafer lot level traceability, so that you know that every wafer lot that we have worked through, every wafer lot or part that you purchase is going to survive, and once it actually gets up on orbit. We do TID testing per lot, as well as benchmark single event latch up at product release for these commercial space low products. And then we also target no MAT tin to kind of mitigate the concerns with tin whiskering. So that can come in either the form of tin lead solder balls for BGA type packages, or that could be nickel palladium gold type lead frames to eliminate the need for matte tin. Additionally, we also do extended temperature testing where the process allows us to do so, as well as probably an important one, particularly if you have optics in the mix, outgas testing to make sure that any of the either the mold compounds or any of the other materials used in those commercial packages do not actually outgas and provide any potential hazards or I guess dangers or problems for any optical components that you might have within the satellite system. When we move on to commercial space high, it's everything that you get with commercial space low and then more. So things like 100% lot burn-in, all of the devices are now serialized so that we can do pre and post burn-in deltas on a per device basis. We do a wafer lot acceptance test similar to what we would do with QMLV type products. And then we also do single event latch up testing on per wafer lot basis on commercial space high products. And if you look at this and kind of compare to traditional space, you might say, well, this looks extremely similar to QMLV. Why is this any, or, what's the benefit of commercial space high then? And really there are two things. One, there are newer products nowadays. Some of the performance that you can get out of them comes from the packaging that they are actually, packaged in. So things like the high-speed converters, if we were to take that and put it into a ceramic hermetic package, some of the performance that has been built into the package that was released with the commercial version, you lose some of that performance. And that's also particularly true with things like power management devices, whether it be battery management or other things. Particularly things like switching regulators. Nowadays, a lot of that performance is built into the package. And so we want to bring these types of products into space because people are demanding them, but we don't want to lose that performance. We want to get the best performance out of the part possible. The other big benefit for any other product that maybe isn't as dependent on the packaging is those plastic packages are often much smaller than you would see with a ceramic hermetic package. And kind of as we've mentioned before, small sats and CubeSats are becoming more ubiquitous, and any amount of PCB space that you can save is going to be significant, and it leads to a smaller satellite, which is therefore more lightweight, which is therefore less expensive to launch. And in addition, there's some cost savings involved with using these plastic packages as opposed to ceramic hermetic. So there is cost savings there. But really, when it comes to commercial space in general, some of the cost savings tend to start to snowball when you start looking at the greater picture. So kind of in summary, what we've discussed is the industry's in a period of very rapid change and evolution. And there are a lot of rising pressures to reduce cost and development times, both from the satellite perspective, as well as being able to launch quickly. And increasing demand for more data at higher rates is calling for the latest and greatest technology that the industry can offer. And commercial space kind of allows us to execute on those much faster than we would otherwise. And then ADI's commercial space products program is designed to kind of meet the shifting market demands while maintaining reliability in the harsh environments of space, and maintaining that confidence that you know that the products that you're ordering, that you're buying, are going to survive once they actually get up on orbit. You're not going to have to worry about failures due to radiation, for example. So with that, I'd like to open the floor up to questions. And Steve, do we have anything in the Q&A section?
So we don't have anything in the Q&A, but we do have some question submissions. We've got two questions there. The first question is, how does the typical pricing compare between commercial grade product, commercial space, and traditional QMLV products?
Chris or Sean, do either of y'all want to kind of take that one?
Sure, this is Sean Darcy. I'll take that one. So what the objective is when we actually have created these new portfolios is the value and the cost and the qualification requirement to make a QMLV or a Class S or Class K type space part, of course, draws a lot more labor and cost, but also drives a much higher price. So those are up at the very high end of the pricing spectrum. After that, then we also created, as Christian mentioned, our two commercial space flows, low and high, and those are meant to be lower priced, but also support much higher volumes across the market. Conversely, of course, those come with less screening and less development qualification costs that go with it. We still think they provide excellent value across the spectrum. So while they have a slight increase above maybe an enhanced plastic or a military grade product, they are far less expensive and more economical than, for example, a QMLV part.
All right, and the second question is, what commercial space products are already available?
So I can kind of take that one. We have one that we released earlier this year. We've taken the AD9361 RF transceiver and released that under our commercial space low flow. So that one is now available. But if you are interested in kind of learning more on what's coming down the pipeline, you can feel free to reach out to us either via the Nsrec booth, or you can send us an email at space@analog.com. And we'd be happy to kind of share information.